Hey, good afternoon, everyone. Welcome back from spring break. I hope you all had a relaxing week and that you're ready to get back into things. So quick reminder is that Lab 4 is due on Thursday, and then Lab 5 is going to be due next Thursday. All right, so last time, if you recall, what we did was we learned how it is that we are going to build our beta. And so we learned about all the different pieces that we have to put together in order to make the data path work. And we found that because it's a RISC-reduced instruction set computer, the amount of hardware that we needed in order to make this happen was actually pretty simple. And there were a lot of pieces that we were able to reuse. So what we're going to focus on today are these boxes in yellow, which are our memories. And if we look at our whole design of the beta and think of it in terms of the number of MOSFETs that are required for the entire thing, you basically find that the memory takes up the majority of those transistors. Similarly, as far as execution time is concerned, accesses to memory are what dominate the execution time. And so in many ways, we can kind of think of our beta as a memory machine rather than a computing machine. And so today what we're going to focus on is what kind of memories are available to us so that we can try to deal with some of the issues of size, access time, and see what the trade-offs are as we explore this realm. So before we move on, just remember that for every single cycle of in our beta, we need to access the instruction memory, so that's at least one memory fetch. And even though some of our data is going to be stored in registers, eventually all the data that we really need to keep track of is going to be put back in memory. So we're also going to be doing loads and stores from our data memory. So let's see, how we can go about dealing with the bottlenecks that are associated with the paths that communicate with these memories. Okay, so there are lots of different technologies for building memories. And they vary in many different parameters. They vary in their capacity, in their access latency, they vary in bandwidth, energy consumption, and certainly in cost. And what we also find is that different memories end up being good for different applications. And so today we're going to explore this array of different types of memories and try to get a better understanding of when you would use each kind. So we start off with these registers. So registers are what we use as part of our data path. So we already learned that registers are very fast. In fact, if you look at their latency, it's on the order of 20 picoseconds. So the constraint with registers, though, is that we have to keep the number of registers very small. So we can only use them in order to access up to thousands of bits, so not very many at all. And so we'll use this within our processor data path, but obviously it can't be used to provide us with a lot of capacity. So what we're going to explore next are SRAM and DRAM, which stand for static random access memory and dynamic random access memory. And here what you see is that the numbers, as far as the capacity that's available to us goes up, the cost starts to drop significantly. But the one negative piece is that our latency goes up. And as we continue to explore these different alternatives, we're going to find that that relationship holds. So as we provide ourselves with more capacity, the access time is going to get worse. So the third type of memory we're going to consider today is what's called non-volatile memory. And what this means is that basically even if you if you turn off your power, the data is not lost. And so here you can have things like a hard disk, which is the absolute cheapest form of memory, where we can get tons and tons of capacity at a very, very low cost, but the access time is on the order of tens of milliseconds. Okay, so let's take a closer look at how each one of these works. So we're going to start off with the static RAM. And the structure of the statogram is basically this two-dimensional array where our rows correspond to a location in memory, and the columns are the bits in that location. So in this example here, we have an 8x6 SRAM array. So we have 8 locations, each of them is 6 bits wide. In order to specify which of the locations we want to communicate with, we use this address decoder, and because here we have, in this example, just 8 locations, we need 3 bits to specify which of the locations we want to access. And so we pass this 3-bit address, and what that does is it turns one of these word lines, these horizontal lines, on. The rest of them are all off. So what happens when you turn one of these horizontal lines on is that these SRAM cells that are associated with the word line that you selected are going to now be connected to these vertical lines, which we call bit lines, okay? And on these bit lines, we're going to either read the data that's in the cell, and then that information, it's actually analog data that's going to come through these sense amplifiers so that we can read the data. Or if we want to write the data to them, we're going to put data in here through our drivers. They're going to drive these bit lines, and then that in turn will cause the cells of the selected word to get overwritten. Okay, so let's look at that in a little bit more detail. So what does an SRAM cell consist of? Okay, so at the heart of that array were these little SRAM cells, and each of them consists of 6 MOSFETs, okay? We have 2 inverters, which are what's used in order to basically give us what we call a bistable element. So what does that mean? Bistable means that it has 2 stable states. So in this top configuration here, it means we're storing VDD, or 1, and in this bottom configuration, we're storing a 0, okay? Now, because we have these inverters that are attached in this feedback loop, what it means is that we're constantly regenerating our value that we're storing. And so even if a little bit of noise is introduced on our wires, it's still going to be okay because we're going to reproduce a valid output based on what we learned earlier in the term of how we can get rid of noise by producing outputs that are always better than their inputs. So far so good. So we've got 4 transistors so far. And then we have 2 more, which we call access transistors or access FETs. And what these do is these basically allow you to connect the data that you have stored in the cell to those vertical bit lines. And so we have 2 bit lines. One is going to be for the actual value, and then we have bit line bar, which holds the opposite or the negation of that value. All right, so how do we do a read? The first thing that we need to do in order to read from an SRAM memory is that we're going to pre-charge all of these bit lines to VDD. Okay, so we're going to set both bit line and bit line bar to 1, and then we're going to stop charging them. At that point, we're going to use our address decoder in order to select one of our word lines. So we select the line that we want to read from. And then when you select that line, what happens is that these access FETs turn on, okay? So they're off on all the other lines, but they're on the line that I selected, which means that the SRAM cells of the word that I selected are now going to be connected to these bit lines. Then what's going to happen is that for the cells that are on, you're going to eventually pull one of these, either the bit line or the bit line bar, down to ground. Okay, that's going to happen very slowly, as you see over here. So here what we had is we had an example where we had a 1 stored, and excuse me, we had a 1 stored, and now we're trying to read it, and so on this side we have a 0, and so when your bit line, which was pre-charged to 1, as it connects over to here, it starts to lose its value, and very slowly it's going to drop down to 0. Okay? So it actually takes quite a bit of time for that to happen. And the reason is because the capacitance on these bit lines is quite high. And so what we do is, instead of waiting for it to get all the way down to 0 before we read the value, we use these sense amplifiers. And what these sense amplifiers do is they notice as soon as one of these two sides starts to go down, it'll detect that and basically turn it into a digital signal. And so at that point, very quickly, you're going to be able to know which side is 1, which side is 0. And so that way, you're able to read the value of your SRAM cell. Okay, so how do we do writes? Writes are similar. The difference now is that we're going to drive our bit lines with the values that we want to write into our cell. Okay, so in this case, the 2 bit lines have 2 different values. If you're going to want to write a 1, then you're going to drive VDD on the positive bit line side and ground on the opposite. If you want to drive a 0, you'll do the reverse. So in this example here, we're trying to drive a 0, which means we'll put ground on our bit line and VDD on bit line bar. Okay, so next, we use our decoder to select which word it is that we want to write to. Okay, and so we've selected one of these. We've now turned our access FETs on for the one that we selected. So once again, the cell is connected to the bit lines. Now in this case, we actually have bit lines that we're continuing to drive. Okay, it's not like in the read case where we just pre-charged them and then stopped. So now what's going to happen is that because the MOSFETs on these bit lines are so much stronger than these tiny little MOSFETs in these inverters, these are going to actually overpower what's in the cell, and so it'll overwrite what's there. And essentially, where most of the work gets done is in this NFET of the side that's trying to pull you down to ground. It's going to even though these 2 things are attached and you've now connected VDD and ground, what's going to happen is that this NFET, because we know that the currents in NFETs are much stronger than currents in PFETs if you have the same dimension, this NFET is going to very quickly pull this value down to ground, even though this little PFET was trying to pull it up to VDD. Okay? And notice here that you also have a threshold loss over this NFET to deal with, which would make you think, maybe I can't get this value all the way up to VDD. But as soon as you get this side down to ground, then what happens is you start to enter your feedback loop, and then immediately the cell itself is going to help you get this value up to VDD. Okay, so well, I guess we went through this already. So basically, just the key to remember is that the one where most of the work is done is on the side where you have, you're trying to pull down to ground because your NFET is more powerful than your PFET. Okay, so far we've looked at SRAMs that can either do one write or they can do one read. They can't do both. So we want to consider if we can augment this architecture to have multiple ports. And we can. Basically, the way that would look is you'd add another decoder to specify, the second location that you want to access. You'd have word lines associated with that decoder. You'd have an extra set of bit lines for every additional port you want to add. You'd have additional drivers and additional detectors here to detect whether the signal is going up or not in order to produce your 0 and 1. So basically, what we see very quickly is that in order to add ports, our SRAM's architecture has to grow significantly. So what's the order of growth here? Well, as far as the word lines are concerned, if we want to go from 1 port to n ports, then the number of word lines we have are going up by a factor of n. Okay, and similarly, our bit lines and our access FETs, we have 2 bit lines for a single port. If we have n of them, we're going to have 2n bit lines, and we're going to have 2 times n access FETs. And so what's this going to do to the size of our SRAM? Well, the height of this array is proportional to the number of these word lines. So if that's going up by a factor of n, our height is going up by a factor of n. The width is proportional to the number of these bit lines. So if the bit lines are going up by a factor of n, we're getting that much wider. So our area is actually going up by a factor of n squared. And so very quickly we get into a situation where the wires start to become the dominating latency in our memories. And so there's only so far that we can take increasing the size of our SRAMs. And so as far as adding, not just increasing them, but adding additional ports. So while it's useful to be able to do things like what we do in our beta of having 2 read ports and 1 write port, you don't want to just go willy-nilly adding as many as possible, because you'll very quickly start to degrade the performance of your SRAM. Okay, so summary of SRAMs. Basically, we have an array of k words by b cells. If this array actually gets bigger, then we might not be just a 2-dimensional array. We might arrange it slightly differently so that the lengths of the wires are minimized. We learned that each cell has a bistable element, which is achieved through this feedback path with your inverters, and it has access transistors that connect it to the bit lines. We do reads by pre-charging the bit lines, then activating the word line and sensing which of the 2 sides went down a little bit. And we do writes by driving the bit lines, again selecting the word line, and this time overpowering the cells. Okay, so that's SRAMs. Now, each of these SRAM cells, however, requires 6 MOSFETs. So we want to ask ourselves, can we do any better than that? What's the smallest number of MOSFETs that we could use in order to still store a value? Any guesses? So let's try to see if we can do it with 1, okay? So the way that dynamic RAM, or DRAM for short, works is that you have this one access FET, and so what this allows you to do is it allows you to connect your bit line to your word line, okay? This time, however, the way that we store our data is using a capacitor, okay? So we put charge on this capacitor, and so if there's charge on it and we detect that, then that means that we're storing a 1. If we want to store a 0, we basically discharge this capacitor. Now, the capacitor is going to be better and better at telling us what the value is if the capacitance is higher. And so we want to look at what are the parameters that affect the capacitance. And so we have 3 parameters. We have the dielectric constant, area, and the thickness of the dielectric of the film. So what we see here is that in order to increase our capacitance, we can either select a different material, and thus making the dielectric constant higher. We can increase our area, or we can make the distance between the 2 plates of the capacitor smaller. So over here on the right, we see kind of what a DRAM cell looks like. And what this is it's basically made up of what we call trench capacitors. And so the way these work is you're kind of digging a trench into the substrate of your integrated circuit. And the deeper you go, the larger area you have, which means the higher capacitance you have. And so notice that you can actually get, pretty big area here without actually affecting the size of your integrated circuit, because you actually have only gone into the substrate, which was already there. And so that's one mechanism that we can use in order to increase our capacity, is by increasing the area. The second thing is the insulator that's used. So we can try to pick a material that's going to lower this dielectric constant. And in addition, we try to make this material as thin as possible so that this value D goes down, once again raising capacitance. So the ultimate effect of that is that we're able to build much, much smaller and denser memories, which are, consist of just a single MOSFET. The negative side of DRAMs is that because you're storing the value in a capacitor, the capacitor actually loses its value over time. There's leakage from that capacitor. And so what that means is that we have to refresh the value that we're storing into that memory location. So every time, just on a regular basis, on the order of milliseconds, we're going to have to refresh the value that we've stored so that it doesn't just disappear on us. Okay, so let's take a look at how writes and reads and writes work for DRAMs. In the case of DRAMs, we're actually going to start with writes because writes are a little bit simpler. So what happens here is you drive your bit line to VDD or ground, depending on what it is that you want to write into your cell. And then you select the word line that you want to actually write to. And then what happens is if you put a VDD over here, that's going to charge your capacitor. If you put ground over here, that's going to discharge your capacitor. And the result is that you've written a 1 or a 0 to your DRAM cell. Now what about reads? So reads, we do a little bit differently. What we do is we pre-charge this line over here to something like VDD over 2, okay, somewhere in the middle between ground and VDD. And then we select the word line that we want to be active. Now what happens is that if this capacitor had a 0 on it, and this is now at VDD over 2, then what's going to happen is that some of this voltage is going to come into the capacitor, and so this voltage is going to go down. And that will indicate that you had a 0 being stored here. On the other hand, if you had a 1 stored here, meaning this was charged, then the voltage here is actually going to go up slightly, and so you'll be able to detect that that was a 1. Okay, and so that's how we go about reading our DRAM cells. So, if you take a closer look, though, at what's happening when you do a read, suppose we had a 1 here, and I put VDD over 2, what happens? Well, we said that I'm taking some of the voltage that's over here, and it's coming over to my bit line. So basically, my reads are destructive. Okay, so I'm taking that voltage that's stored in that DRAM cell away when I read it. So what we have to do is not only regularly refresh our DRAM cells because there's leakage current, but also every time you do a read, you have to write the value that you read right back into your DRAM cell so that it's not actually lost. Okay, so to summarize DRAMs, we basically have a single transistor plus a capacitor. They're much, much smaller than SRAMs, but the negative side of it is that they have destructive reads, and you have to also refresh them. So in order to be able to write back after you do a read, as well as to refresh, you have to add some additional logic in your hardware to be able to do this. The result of that is that DRAMs, while they're much, much smaller than SRAMs, they're also slower than SRAMs. Okay, and so once again, we're seeing that trade-off that we saw at the very beginning of lecture, which is that as we're increasing capacity, we're making our latency get worse. Okay, so now we'll move on to non-volatile storage, which is storage that will maintain its value even if you turn the power off. And the first example of this is what's called flash memory. The way flash memory works is you basically have this floating gate over here, which is surrounded by an insulator, and so you can put some charge onto this floating gate, and because it's completely insulated, that charge is going to stay forever, for years. So then, how do we go about making use of this charge? Well, we essentially place it inside a MOSFET. So here we have an NFET, where the gate, this floating gate lives between the gate of the NFET and your channel. And so the way that this works is if, for example, this floating gate didn't have any charge on it, then you'd be able to just put, a regular voltage, just like you always would on an NFET that would turn it on, and you'd start to see current flowing here from your source to your drain. okay? So the voltage that's required to get that to happen, let's call that voltage V1, if there's no charge on your floating gate. Now suppose that there is a charge on your floating gate. In that case, what's going to happen is you're going to have a higher voltage in order to get current to flow from here to here, because you need to overcome what's the charge that's in this gate, okay? And so in that case, we'll need, let's say, a voltage, call it V2, in order to get current to flow from here to here. But one observation that you can make is that you can actually measure the amount of current that flows from here to here. So if what I do is I put some kind of voltage that's between V1 and V2 on my gate, okay, then I can measure how much current I'm getting, and based on that, I can determine how much charge is on this floating gate. The advantage of that is that basically this allows me to store multiple bits within a single transistor. Okay, and so depending on how much current I'm producing with the voltage that I'm putting at my gate, that's going to tell me how much charge there is, and as a result, that indicates what's the value that I've stored into that flash memory cell. So this is even denser than our dynamic RAM, right, where we had one transistor. Now we have actually multiple values per transistor. But once again, we're getting even slower than we were before, okay? Accessing our flash memory is very slow, especially for writes, because in writes, what you have to do is you have to overcome this insulator that's surrounding this floating gate. And so in order to do that, you need a very high voltage. That actually has two effects. Number one is that it makes writing be pretty slow. And in addition, it has a second negative effect, which is that over time, these flash memory cells actually get ruined. And the reason that they're get ruined is because you're putting so much voltage in that you're actually, over time, start to ruin this insulator that's around the floating gate, and so that after some period of time, it's no longer able to retain that value. Now, we're talking lots and lots of times, so you can use it on the order of 100,000 to 1,000,000 times before you get to this situation, but it is something you need to be concerned about, okay? And so while flash memories are good, they're denser, you know, they do have the negative caveat of having to be replaced, and so it's more costly certainly than our hard disk solution. Okay, so what about our hard disk solution? What does this look like? Hopefully most of you are familiar with your hard disks on your computers, and basically the way that this works is you have these rotating magnetic platters, and then a head that you have to situate in the right position over the platter in order to read the orientation of the magnetization, or to actually change that orientation if you're trying to do a write. And so the reason that these are particularly slow is because it's a mechanical process to move this head to be over the right track that you want to read or write to. And then once you're over the right track, then you start spinning your disk so that you get the correct sector within the track that you're trying to access. So once your head is actually over the correct track and the correct sector, then you can do your read or write, okay? So what you find with hard disks is that they're really, really, really slow. However, if you try to do sequential reads and writes, in other words, try to read many locations of memory that are next to each other, then the rate at which you can access it is not too bad. It's 100 megabytes per second. If, on the other hand, you're just trying to access any random location that has nothing to do with the previous one, then you get a huge hit, and your rate goes down to 100 kilobytes per second, okay? And so, so basically, hard disks are great in the sense that they're super, super cheap. They give us tons and tons of capacity, but as you can see, we've gotten, you know, to the worst situation as far as speed is concerned. Okay, so we basically saw these 5 different types of technologies and their trade-offs. The key being that if we want to reduce our latency, we also reduce the amount of capacity that can be covered by that type of memory. So, there's this fundamental limit that's saying, okay, if I want to have a low latency, my memory has to be small. If I want to have, a large memory, then the latency is going to be long. So we ask ourselves, well, does that have to be the case? Okay. Ideally, what we want is the best of both worlds. Okay. So we want to envision the situation of what we call a memory hierarchy, where you'll have different types of memories making up your entire memory space, so to speak. And the idea is that you would put things that are going to be used frequently into your fast memory, and things that are going to be used infrequently into the slow memory. And so that on average, what ends up happening is that your average access time is actually much closer to the fast memories than it is to the slow ones. So the real question is, well, can we actually do that? How do you figure out, which pieces of data or code need to live in which piece of memory? So there are two approaches to this. The first approach says, well, let me expose this hierarchy. Let me make my programmer know that they have, this super fast SRAM over here, then this slightly slower but much larger DRAM, or, this humongous hard drive over here. And you can say to them, well, as part of your program, use your memory cleverly. So you know what's being used frequently. You know which pieces of data you're going to access multiple times. Make sure to put those in your fast memory. Okay? And so there were actually many believers in this model. Seymour Cray happened to be a strong proponent of them. He is the architect who's responsible for having built supercomputers. And his way of thinking is that basically you want to deal with vectors of data at a time. You bring these vectors of data into your fast memory, you operate on them in the fast memory, and then you move it back to your slower memory once you're done with it. And this actually worked quite well, and in fact there are many benchmarks on these computers that show that that they were able to run quite quickly using this paradigm. However, there is a second approach, which is to hide this hierarchy. So to not make the programmer have to worry about it. And the nice thing about that is, as far as the programmer is concerned, they just have this huge memory and it's fast, right? And they don't have to worry about where the data is going to go. Somehow behind the scenes, it's figured out for them. So how could we do that? Is it possible to actually figure it out without having that knowledge of what exactly your program is doing and how the data is being manipulated? And it turns out that there is a way. And the way that this works is, as we mentioned, our ideal was to have small, fast memories where we keep the pieces of data that we use most often, and then we have larger memories where we keep the pieces of data that aren't used frequently. And the reason that we're able to detect which belongs in which category is this notion of locality. The idea of locality is as follows. It basically says that if I'm accessing location X in memory, then it's very likely that at a time t plus a small delta t, I'm going to access another location that's very close to that one in memory. Okay, and we'll take a closer look at the exact meaning of that in a second. Okay, so what are we saying? We're saying that if I access one location in memory, I'm very likely to access another one that's nearby. And this also plays out in a different way, so that's what we call spatial locality. There's also what's called temporal locality, where what happens is that if we access a particular instruction at some time t, it's also very likely that we're going to access that same instruction at some time t plus delta t. So how does that happen? Why does this actually make sense? So what we're going to do is we're going to look at memory reference patterns to see if we actually believe in this concept of locality. We're going to start off with code, okay? So what do our instructions look like? Suppose that I'm executing a procedure, right? If I'm executing the first instruction in my procedure, then chances are that I'm executing the rest of the procedure as well, right? And so if that procedure is stored in memory in consecutive locations, then what's going to end up happening is that the way that I'm accessing the data that's associated with this procedure is sequentially. So these pieces of code live one next to the other in my memory. Okay, which means that if I bring this piece of code into my fast memory, then it would probably be good for me to also bring the ones nearby, because chances are that I'm going to need those as well. Okay, so there are a couple different types of accesses that we see here. So first of all, something like this is just, sequential one after the other. What do you think these three things here mean together? What's going on here in our code? A loop, right? So basically the way a loop works is we run a few instructions and then we repeat them, right? And so, there are many different instances like this in our code. Sometimes we'll have some branches which take us to another piece of code, but then once again, you're going to see this sequential type of access, okay? Now, what about the data that's on our stack? When we execute procedures, what happens to our stack? We make basically a stack frame, right? We put our arguments onto the stack, we store our base pointer, our linkage pointer, and any kind of local variables. And when we execute a particular instance of the procedure, we're operating on a very small portion of our stack, okay? And so that's what we see here. We basically see that over a particular period of time, we're operating on a very small portion of the stack. Then as time goes by, we go on to another portion, and then another and another. But the bottom line is that it doesn't change that quickly. And finally, data. So how does data work? Data accesses can be of the form something like this. What this might mean is, let's suppose that I have an object that has multiple elements in it. If I access one of those elements, chances are that I'm also going to be accessing the other elements. And so what I end up seeing here is that my data accesses are also for locations that are close to each other in memory. Similarly, another very common type of access is this sequential one here. Can anyone take a guess as to what that might correspond to? I think I heard something, but it wasn't loud enough. Arrays, exactly. Okay, so how do we access arrays? Arrays are basically locations in memory that are that are consecutive, and you generally, when you do something with an array, you do something with one element and then the next and then the next and so on and so forth. And so you'll see this type of behavior when you access an array. Something like this could be, let's say, I'm copying an array from one location to another, but once again, the point is that in our data as well, we also see this type of behavior where you exhibit locality, okay? So we can really make use of this idea of putting the things that are going to be used frequently into our fast memory. And what we actually find is that if you try to figure out what the working set is of how many locations in memory am I actually accessing over a particular period of time, you'll find this nice looking graph here, which shows you that after you get beyond a particular threshold of the amount of time that you're looking at, the size of your working set is actually pretty constant. So what does this mean? This means that I can, as long as I have a fast memory that can fit that working set size S, then I'm going to be able to get the best of those both worlds. I'm going to be able to access my most locations very quickly, and on a rare occasion, I'll have to go to slower memory. Okay, so what does this bring us to? This brings us to the concept of caches, okay? We're going to continue with caches in next lecture as well, but today we're just going to start introducing the idea. So what's the idea behind a cache? A cache is basically a smaller memory that's faster, and that enables you to access a larger memory seemingly more quickly, okay? And the way that it does this is it exploits the idea of locality. And the idea is that if something is in your cache, then you're going to be able to fetch it very, very quickly. If it's not in your cache, you'll pay, an upfront price once, but because of locality, chances are that you're going to need to access that location again in the not so distant future. And if you happen to actually bring a block of data into your cache, then it's also the case that the instruction that's immediately following, you're already brought into your cache, and so that it's going to be there the next time you try to access that location. And so by making use of locality, we can actually make it be the case that very often we're going to be successful in finding our data in that smaller, faster memory, which we call a cache. And in fact, this idea of caching is used in many, many places. If you think, for example, about your web browsers, right? Your web browsers remember which pages you visited, and what they do is they cache that information. And so next time you go to look for that web page, if the browser already got it for you in the past, and the web page hasn't changed, then it's going to be able to serve that web page to you much, much more quickly because it has the data already in that fast memory. If the data changed, then it might require a longer period of time. Okay, so we have this really large sort of memory hierarchy, and what you'll find in general is that you have different levels of this hierarchy that, that each one of these is essentially a cache for the one underneath. So for example, your level 3 cache is a cache for your main memory, while your main memory is a cache for your flash drive, and so on and so forth. And as you go down this table, your access times go up, but the amount of capacity that you can handle goes up significantly as together with that. So they're actually, you can kind of think of caches as being implemented in two different ways. Today, we're focusing on hardware caches, which are the ones that are going to be built on chip. A few lectures from now, we're actually going to get into this concept of software caches, where we're going to introduce the idea of virtual memory, where it'll seem like you have more memory than you actually have, and we'll get to that soon. But today, we're going to focus on this piece right here, and the bottom line is that regardless of how it's implemented, these trade-offs continue to reoccur. Okay, so how does a cache access work? In a simple model, we have a processor here, we have our cache, and we have our main memory. Now, suppose that the processor wants to do a load of address 6004. Two options exist. Either the data is in my cache, okay? If it's in my cache, then we call that a cache hit, okay? And so I basically went to my cache, I said, is this 6004 address in the cache? It says yes, and then it sends that data back, okay? However, it's possible that that's not the case, and instead I get a cache miss. So notice that when I get a cache miss, I still had to pay the cost of having to first check if it was in my cache, right? So I now have a little bit of a penalty because I pay the time to look in my cache, and then I also have to go to main memory. So suppose, I looked for address 6034, I didn't find it in my cache, I then proceed onto my main memory, get it from there, the data is brought back into my cache, and then fed back to the processor. So as far as this processor is concerned, you'll notice that there also, the latencies of getting the data are not necessarily equal, and the processor is going to have to be able to deal with that. But the key is to think about, well, how well can we actually do with our caches? And so what we do is we introduce some metrics related to caches. The first two are called hit ratio and miss ratio. Hit ratio and miss ratio are basically giving us a sense for how often is it the case that we are finding our data in the faster, smaller memory, okay? So if you think about all of your accesses, that's your hits plus your misses. Hits over hits plus misses is your hit rate. 1 minus that is your miss rate, or another way to say that it's misses over hits plus misses. And using this, we can come up with an equation for the average memory access time, which is on average, how long does it take us to access our memory? And what we find is that basically you always pay your hit time, right, which is the time that it takes to access your cache. And then in the situations where you have a miss, which is this miss ratio, you also pay an additional miss penalty, which is the amount of time that it takes you to then go to main memory. Okay? So this gives us a sense of how we can go about measuring how well we're doing. And we can give ourselves kind of target average memory access times that in order to achieve those targets, it might make some predictions on what kind of hit rates do we need to have in our cache so that things work as we expect. You could also apply this, this equation recursively. So as we said, we can have, multiple levels of caches. And so if you had, a level 1 and a level 2 cache, you would simply plug in the values for level 1, and then you do the same thing recursively for level 2, and so on. And so this equation continues to work. So let's look at a simple example to see if, we can make some sense of these numbers. So we have our processor, our cache, and our main memory. And as expected, our cache is way faster than our main memory. It takes 4 cycles to get something from our cache, whereas it takes 100 cycles to get it from main memory. So the first question we want to ask ourselves is, what kind of a hit ratio do we need to have in order to just break even? So what does break even mean? Break even means that we're doing as well after adding this cache as we were doing with just main memory. Okay, so to do just as well, that just means that our average memory access time has to be 100. So we take, the hit rate time plus the miss rate times 100, and that shows us that we really don't need a very high hit rate at all, just 4%, in order to at least break even. Okay, but clearly we want to do a lot better than just breaking even, right? We want to actually end up making our memory look like it's a fast memory. So suppose, for example, that I wanted to figure out my hit rate such that my average memory access time would be 5 cycles, right? So it's a little bit worse than getting a hit 100% of the time in my cache, but it's not terribly worse. So how high of a hit rate do we think that we need in order to do that? And so once again, we can plug in our numbers, and what we find is that we need a very high hit rate. It needs to be 99% in order to be able to make our average memory access time that good, okay? And so these equations give us a sense for being able to understand the different parameters, how well we can do and how high do we need our hit rates to be in order to get those achievements. And what's great, though, is that this concept of locality actually makes it very much be the case that we're much more in this domain than in this domain. So our hit rates are actually quite high. Okay, so next time we're going to get into the details of what caches look like. But just to finish things off today, very quickly, I'm going to just give you a basic algorithm for what a cache looks like. So the idea is you have your CPU on one end, your main memory that has all of your data on the other end, and then you have this fast cache in the middle. Now remember that your cache does not contain all the locations in memory. So in addition to having some data, you have to store some information about the address of the location that's that's in the cache. Okay, so if, for example, I have address A in my cache, I'm going to have a tag that says this is the value of location A, and I'm going to have the data associated with it. So now, if I try to access memory location X, what I'm first going to do is I'm going to try to see if X is in one of the tags in my cache. Okay, so can I find it in my cache? So if I get a hit, that means that it was in my cache. That means that one of these tags was equal to X, And so then I simply need to read the data that's associated with that tag that I matched, okay? Similarly, if I'm trying to do a write, then I would basically, let's say I was trying to write to tag A, to address A, I would now change the data that's associated with tag A in my cache to be this new value. Now, writes are a little bit more complicated because it's not enough to just store the updated value here. Eventually, I need to get that new value back into main memory, okay? So we'll talk about write strategies at a later time, but basically the idea is that you would write it to your cache and then you would also start writing it to main memory. But what's the advantage of writing it to your cache? Suppose that now, a couple instructions from now, I want to access address A again. What happens? This time it's there, right? Even if I had a miss the first time, the second time I'm going to get a hit because I brought it into my cache, okay? So what happens when I get a miss? If I have a miss, then that means that none of my tags match the address that I'm looking for. So then what I have to do is I have to decide which line of my cache I'm going to bring my data into, okay? So generally our cache is full, which means that in order to bring something into my cache, I have to take something else out. So I have to pick what's the item that I'm going to take out. That's what we refer to by this replacement strategy, which again we'll get into in more detail. And then I read what the piece of data that I'm looking for, and I bring it into my cache, and I set my tag accordingly. If I'm doing a write, then I would write to that location, and again, I would initiate the write back to main memory, but the point is that the next time I try to access that location, X, it's going to be in my cache, so my next access is going to be fast. Okay? So that's it for today. And next time, we'll see how we go about actually addressing the cache, figuring out whether it's there or not, and looking at different types of architectures for our caches.